Looking more at tangents to circles, that is. Remember, a tangent is a line that intersects a circle at exactly one point, that point of tangency. Today we're looking at common tangents. Common tangent is tangent to two circles. Common tangents can be internal tangents or external tangents. Here's some internal common tangents right there. Common tangent, tangent to two circles. It can be internal where they intersect each other between the two circles, or it can be external where they do not intersect each other between the two circles. Remember a very important theorem which I know a lot of us thought was so super simple the first time we heard it. Still is simple, but we've probably forgotten it. If two tangent segments are drawn to a circle from the same exterior point, then they are congruent. Let's put all this stuff together. Take a look at this example here. Right here, an exterior point, two tangent segments here from QN and RN, QN and QR are tangents to the same circle that share an exterior point. They're tangent segments. I'm essentially ignoring the rest of this tangent, and I'm just worrying about those segments right there. Those segments must be congruent because two tangent segments sharing an exterior endpoint must be congruent. So that means that x must be 12. It must be 12. It has to be 12. And I should be able to back that up. Over here also involves x. And notice QP, QM is the same situation going on over here. So 2x minus 10 must equal x plus 2. And so we should get x is 12 from this. Subtract x over, we get x. Add 10 over, we get 12. We've seen it two ways. X is 12. But that's not necessarily the question at hand here. We want to find the length of MQ. Where's MQ? MQ is right here. And so all I need to do is take 12, plug it in for x. 2 times 12 minus 10 gives me 14. MQ is 14 units. Two circles can be tangent to each other. Two tangent circles, these are coplanar circles that intersect at exactly one point. Tangent circles intersect each other at exactly one point. Tangent circles can be internally tangent or externally tangent. Internally tangent, one circle is inside of the other and they're still intersecting at one point. Externally tangent, one is not inside of the other. They're external, but they still share one common point. In both cases, the radii of the two circles are collinear. If I draw a radius to that point of tangency for both circles, that second one was not such a great, come on, beautiful line. Those two form a perfectly straight line. Same thing here. If I draw the radius of the big circle and the radius of the small circle, who would have guessed? They are collinear. They are part of the same line. In this diagram, circle Q is tangent to circle M, and NP is tangent to circle Q. NP is tangent to circle Q, so P is the point of tangency. The radius of Q is 5 centimeters. The radius of M is 2 centimeters, so that's 2, that's 2. Find the area of triangle QNP to the nearest square centimeter. Well, QNP is a right triangle because our radius is meeting the point of tangency, and so that radii and that tangent form a right angle. So this is a right triangle here. I see the hypotenuse is 9. If I just draw out this right triangle right there, the hypotenuse must be 9. 5 plus 2 plus 2. The radii plus the radii plus that radii is 9. This is 5. If I rotate this. So I make 5 the base, 9 is the hypotenuse. If I find that third side of my right triangle, I found the height. I know that a squared, I'm going to let that be a, that's what I'm going to do. I know that a squared plus b squared is equal to c squared. And so a squared plus 25 equals 81. If I finish out that Pythagorean theorem right there, I'm just going to go ahead and round this because that's what I want my final answer to be. This is about 7.48 centimeters. So I know that the height is 7.48 centimeters. I know the base is 5. The area of my triangle is 1/2 the base times the height. If I type all this in, I get about, to the nearest square centimeter, about 19 square centimeters. Told me to round to the nearest square centimeter. I would typically go two decimal places, but it just said near square centimeters. So who am I to argue with the question? Who am I? All right, here we go. Next, it says a car has a timing belt that consists of 2 pulleys and a belt. As shown in the diagram, the belt runs around the 2 pulleys and is tangent to both of them. The dotted segments JI and JK have been drawn into diagram to assist in finding the distance between the 2 pulleys. Find IH and KL. Okay? Well, I know that HJ would have to be congruent to LJ. I know those would have to be congruent segments. Ignoring that circle completely, I know that those 2 segments would have to be congruent. I know that JI is congruent to JL, so by my segment addition postulate, what's left over here, IH must be congruent to KL. Those 2 must be congruent to each other. So if I take away these 2 congruent pieces from these 2 congruent pieces, these 2 pieces must, what's remaining, still be congruent. So I know their measures must equal. 1/6 x plus 1 must equal x over 2. I can use this to find x, and then I can plug it in to find the measures of these segments. I'm going to get all the x's on the same side. Well, this is the same thing as x over 6. 1/6 x, the same thing as x over 6. So if I subtract it over, I have 1 equals x over 2 minus x over 6. This is 3x over 6 minus x over 6, which gives me 2x over 6. 1 equals 2x over 6, which is the same thing as x over 3. 1 equals x over 3. X must equal 3, because 3 divided by 3 is 1. When I plug it back in, this is 3 over 2 feet, or 1.5 feet. I know they're both going to be the same. Both of them are the same because they're congruent, so they're both 1.5 feet.